Boldly going where no science show has gone before. The Naked Scientists.
Hello, well this week, how octopodes, or octopuses, whichever is your preference, may have temper tantrums. We'll find out why shortly. Why some people are genetically wired to feel more pain, and how scientists have used a brain scanner to see what someone is imagining in their mind's eye. Hello, welcome to this week's Naked Scientists. I'm Chris Smith, and also here this week is Helen Scales.
Hello, yes indeed, and this week we were also answering your science questions, and lots of them too, because it's our science question and answer extravaganza. Stay tuned to find out how odour-abating shoes insoles work, why hot and cold water sound different when you pour them, and they really do. Give it a try if you don't believe us. And why does paint colour change when it dries? The answers to all of those are on the way. And of course, if you've got a question you'd like us to look at, then send it in. The details will be coming along just in a moment.
Thank you very much, Helen. Also, later on in the show, we'll catch up with what's been happening at the Cambridge Science Festival. That's going on at the moment. And Ben and Dave are going to build for us a flame tornado. Intriguing it certainly is. Stay tuned to find out how it works. Meanwhile, if you'd like to get in touch with us, the email address is chris@thenakedscientist.com, or you can send us a tweet on Twitter. It's @NakedScientists.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
I'm going to kick things off this week with the wonderful, intelligent marine creatures, the octopuses, or the octopodes, if you like, another way of saying it, and a group of scientists who have been pushing high-definition TV screens up to the side of an octopus's aquarium tank and showing them images of crabs and other octopuses, and revealing that these wonderful creatures undergo major mood swings, ranging from glum to excitable and occasionally aggressive. Well, previous attempts to show moving pictures to octopuses have failed, and that's probably because the old-style cathode ray TV screens only show pictures 26 times a second, and that isn't fast enough for the sophisticated eyes of the octopuses, and they probably only saw sort of incomprehensible blurs, so it really didn't make any sense to them what they were looking at. Now, Renata Pronk and colleagues from Macquarie University in Australia decided to try octopuses on the brand new generation of liquid crystal high-definition TV screens, and with a bit of trial and error, they discovered that octopuses do respond to images showing at a rate of 50 frames a second. Now, they were working with a species that lives in Sydney Harbour called Octopus trichus, and that's commonly called the gloomy octopus, which is
sounds appropriate.
A very appropriate name for this study.
So just to recap then, you've got an octopus sitting in a tank and an LCD screen against the side of the tank, and there are various pictures being flashed at the octopus.
That's right. And the question is, can they see it and do they respond to it?
What are they showing them? So
they started off showing them pictures of crabs, and that's some of their favourite food. And what happened was, when they started using these high-def HD TVs, the octopuses would leap up and try and attack these pictures, assuming, therefore, that they thought they were real crabs and they were worth having a go at to eat. They also showed films of other octopuses, and then, mostly, they would dash to the back of the tank and try and hide from them, from a competing octopus. Now, this study, which appears in the Journal of Experimental Biology, in that the team basically repeated these tests over the course of several weeks. And this is when they uncovered these mood swings of the octopuses. Because in the same day, an individual octopus reacted in a consistent way to the same pictures of crabs or other octopuses. But later in the same week, they actually quite often showed different behaviour. Some animals were initially quite excitable, and then on another occasion they were quite gloomy and much less enthusiastic. So essentially what they're showing is that octopuses may have some kind of personality, but it isn't really consistent over time. And you get one on a bad day, and you might have an extremely grumpy octopus, but later on, in fact, it might be quite excited and friendly. And now that Pronk and the team have discovered they can use these TV screens, there's all sorts of other things they can now do. They've figured out how to play octopus movies, and they're really excited about going in and looking more at these extraordinary, intelligent animals and finding out more about them, like how do they communicate, do they learn from each other? All sorts of possibilities are now opened up.
Why do they have such a big brain? Because they do, don't they? They can do things like figure out how to open jars and unscrew screw caps and things. Why should they be so intelligent? How does that help them in the wild?
Well, it's all about problem solving. They're able to solve problems about the world that they live in to find themselves food. Yes, OK, they can open jars. Jars don't naturally occur in the wild, but it reflects on their ability to solve other problems that are relevant to them. And for some reason, somewhere along the evolutionary line, these molluscs have evolved and been able to evolve extremely large brains and extreme intelligence. You could ask the same questions of people. Why are we intelligent?
Or not, in some cases. Thank you, Helen. Now, also this week, scientists have discovered that gene sequences can affect how you perceive or experience pain. Now, the story actually goes back a few years. It's a researcher called Jeff Woods, who's based in Cambridge at the Cambridge Institute for Medical Research, and he published a paper when he went to Pakistan. He found a number of families, of children especially, who didn't appear to be able to experience pain at all. And they would do things like put their hands into boiling water. One of them even jumped off a roof to impress his friends. And they would sustain these terrible injuries, but at no time were they ever in pain. And Jeff Woods obviously realised this is quite important. There must be something that's being passed on in these families that gives them this ability, this disadvantage, you could say. So they studied the DNA of these people and they found a gene which is called SCN9A. And what this gene does is it codes for a sodium channel, a little pore, which is present on the nerve fibres called C fibres that are important for sensing pain. And in these families, this gene wasn't working properly, which is why they couldn't feel any pain. But what the researchers wondered was, well, OK, if you take the gene away or stop it working, you can't feel any pain, but could there be different forms of it in the population, meaning that different people who carry a different form of it may therefore feel pain differently from each other? So they did this intriguing study where they had 578 people who had arthritis. They asked them how bad their arthritis pain was, and they then compared their reports of how bad their pain was with X-ray images of their joints so they could work out how bad the arthritis was. And then they compared those results with whether or not these people had certain sequences of this SCN9A gene. And what they found were there were two different forms of the gene. There's one called the A form, which is quite rare, and these people tended to report worse pain for having the same amount of arthritis, and another group of people reported less pain. They had what's called the G form. So that looked interesting. They then checked that result by testing people who had backache and found exactly the same result for sciatica. And then in a third test, they actually got some female volunteers and subjected them to some painful stimuli and found that people who had the A form of this gene experience more pain than people who had the G form. And so what this is suggesting is that there are people in the population who feel pain differently based on the genes they carry.
And this is pain, it's not just senses. I mean, these people who can't feel pain can feel someone touching them, can they still? It's a different form of sense, is it?
It's specific and unique to these little C fibres, the very tiny fibres that specifically signal things like burning or anything that basically triggers pain sensations when you do something to the body. Light touch, which is tickling and just gentle stroking of the skin or ruffling someone's hair, for example, that's low threshold mechanoreceptive stimulation, and that is signalled by a different class of nerve fibres, so that still is intact. So this is very interesting. It says now you can get a handle on how the body interprets pain and maybe go ahead to test people to see what drugs would work best in them, or better still, make drugs that are specific for certain people and will therefore treat pain better in them than others, because as we're finding increasingly in medicine, genetically speaking, one size does not fit all.
Absolutely. And they always say that women don't feel as much pain as men. I wonder if they're going to find out that that is true.
Maybe they're just better at putting up with it. My wife puts up with me. I mean,
absolutely.
Says a lot, doesn't it?
Now, back to the animal world and eyeless scorpions that live in deep caves in Mexico that have returned to the light and regained their ability to see, showing rather amazingly that having a very specialised way of life isn't always an evolutionary blind alley. Now, Lorenzo Prendini from the American Museum of Natural History in New York leads a team who've been studying a group of closely related scorpions, many of which have lost their eyesight and become very pale and unpigmented. And these are both adaptations to life in dark, sunless caves. Well, Prendini and the team scrutinised nearly 200 physical characteristics of these scorpions to work out how closely related individual species are. And this included mapping the arrangement of very tiny hairs on their pedipalps, otherwise known as those large pincers at the front of them. And they used this data to build a family tree, and it revealed that the generalist species living closer to the surface, under stones and amongst leaf litter, actually evolved independently more than once from cave-dwelling ancestors.
Oh, wow. So if they can see, that tells you they must have re-evolved the ability to see.
Absolutely.
Because they got it from these ones that were blind.
Absolutely. And up until now, it's really been widely assumed that when a species evolves specialist characteristics for a particular environment, such as blindness in caves, then they can't reverse that and that become less specialised again. But that's just what we've seen happening in these scorpions. And scorpions have been around for a very long time, 450 million years, and today there's about 2,000 of them, but only 23 are known to live in dark caves, so-called troglobites. That's a great word. There's a word for you today. And the deepest ones are down to about 1 kilometre. But now it's really shown that they've got this flexibility, and the ones that have evolved to live in caves haven't necessarily condemned future generations to remain stuck in the dark, and that losing your eyesight isn't always an evolutionary dead end.
And over time, how long in evolutionary time separates the ones that live on the surface and have got their eyes back from the ones that lost their vision and live in these caves? So how long has it taken to get that back?
Reasonably recently. Only one of the things that pinpoints what was going on is that lots of the surface dwellers, in fact, went extinct around about the same time as the dinosaurs. And this, if we remember, is in Mexico, which is close to where that meteorite came down. And whether or not it had anything to do with the dinosaurs, chances are it probably wiped out these surface-dwelling scorpions. So since then, the ones deep down survived and have re-evolved back up to the surface in the last, say, 65 million years.
Isn't the world a wonderful place? Thank you, Helen. Well, also in the news this week, researchers at University College London have developed a way to read a person's thoughts and basically see what they're seeing in their mind's eye using a brain scanner. And Dr. Demis Hassabis is behind this study, and he's with us now. Hello, Demis.
Hello.
Welcome to The Naked Scientist. Tell us, if you would, first of all, what it is you actually have discovered.
Yes, what we did in this study was to basically get volunteers to view 3 short video clips. These are video clips of sort of everyday common events, like someone posting a letter or someone throwing a piece of trash in a bin. And then what we did is we asked them to memorize those video clips in as much detail as possible. And then a little short while later, they were placed in the scanner and they were asked to freely recall those 3 memories in any order they wanted to and as many times as they wanted to. And then after the scanning, we analyzed their brain scans, and we found we were able to tell which one of the 3 memories they were recalling and at which time at an above chance level.
What was the scanner seeing?
So the scanner was, we were focusing on this small region of the brain called the hippocampus that is known to be essential for this kind of memory. And what we do is we use quite sophisticated machine learning algorithms to try and spot patterns in people's brain scans. And that's what we were able to do here with just the activity patterns in this region called the hippocampus. And we were able to tell from that which memory someone was recalling.
How is the brain playing out that memory through that brain structure in a way that you're able to eavesdrop on?
So what we think is going on is that when they first see these videos in the training session, the hippocampus is responsible for laying down a memory trace, if you like, or a copy of that memory. So that's what allows you to remember something in the future, is that you basically reactivate that memory trace. So what we've done here is sort of try and investigate that memory trace directly and come up with a technique that allows us to look at that memory trace directly in vivo, in a functioning human brain.
And how does this inform our understanding of how that part of the brain actually works, and presumably also how we then extend that into what happens when it goes wrong with ageing and dementia and things?
Yeah, so what we're really interested in, and this study is part of a program of studies that are investigating the fundamental structure of memory. What we'd like to know is things like what aspects of an experience are preferentially recorded by the brain. So obviously these are important questions, because if we can understand how the brain does that, then maybe we can help form therapies for, say, people who have disorders such as Alzheimer's or dementia, where we can try and enhance their memory for the things that they need to remember over and above other stuff that's not so essential to them.
And could you extrapolate the study to look into other modalities, other aspects of memory? You just asked people to watch 3 short films, but could you make it much more detailed? How far do you think you could take this?
Yeah, so that's what we're planning to do next, and in the process of doing at the moment is extending it further into now looking at whether, for example, it's the content of a memory or the context, so i.e. what happened or where it happened, that actually best defines the memory. And that's the start of actually breaking down memories into their components, so we can actually eventually start looking at which features or which aspects of an experience that the brain is coding for.
But of course, it is a little bit artificial because your system had to learn from these people first in order to know what it was looking for and then record back when they did their free imagination and match the two things together. It's a bit further down the line before presumably you'll be able to put someone in a scanner and then work out what they're thinking about without having pre-learned.
Yes, that's right. We're a long way away from creating some kind of general purpose, mind-reading machine or something. In that, as you say, what we did here is that these are three predefined memories that we know, that the volunteer is going to choose between. And also, even then, we're not 100% accurate. So very much at the moment, it's still fundamental research rather than any kind of application such as that.
So the HMRC, the Inland Revenue, are going to have to wait a little while before they can tell whether people are being absolutely honest with their tax returns in future.
That's right.
Demis, thank you very much.
Thank you.
That's Dr. Demis Hassabis. He's at University College London. If you'd like to read a bit more about the paper he was discussing that he and his colleagues have published, it's in the journal Current Biology this week.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientists. It's with Chris Smith and with Helen Scales. It's our science phone-in extravaganza this week, and so we're answering all your science questions for you. Helen, I have one to kick off, an easy start of a 10, I hope, which is, why do submariners' ears go pop? And do they indeed? Wonders Andrea Lewis. She's actually in Hobart in Tasmania.
Great question, and I have to just say I'm glad I've never been in a submarine, because I find the whole idea completely terrifying, being in a metal box at the bottom of the sea, much as I love the ocean. Well, the answer is no, there is probably don't pop, because in fact, unlike a scuba diver who takes down a tank of air and breathes it at pressure that is equal to the water around them, which becomes a very high pressure around you very quickly as you go down, submarines are pressurised so that really inside them they are maintaining atmospheric pressure, only at 1 atmospheric pressure, the unit at which we measure pressure, whereas when you're scuba diving you could be breathing air at something more like 20 atmospheres, much more concentrated, and it's that pressure that makes your ears pop, and you haven't got that. You may get a bit of compression as you're going down in a submarine, as some of that pressure from the water is pushing in on the metal structure and the air inside. But I think that's fairly minor. I imagine they build submarines fairly tough so that they can withstand all this pressure without collapsing inwards. So no, they don't have popping ears. And interestingly and importantly, it means that if you have an accident deep down and you have to escape from a submarine, you won't get the bends because you haven't been breathing air at pressure. You haven't filled up your system with nitrogen, which is the main problem, which will then bubble out of your body, of your blood, if you're scuba diving and you come up too quickly. Same thing doesn't happen with submariners. They actually train to be able to hold their breath for long enough to swim a long way up from the bottom of the seabed and survive if there's a problem down below.
Brilliant answer. Thank you, Helen. And of course, the reason you get that horrible sensation, divers like you call it the squeeze or a squeeze, don't you?
Yeah, and you get around it by holding your nose and blowing, which you can do, but don't do it when you're not underwater. And it equalises the pressure in your eustachian tubes, which is the bit that links your ears into your nasal passages, and you can equalise the pressure on your eardrum. And it's very painful, and you can burst your eardrum if you don't do that as you're going down. So it's very important that you do it.
Because, of course, when you're coming up again, if you've put air into your middle ear at pressure down there, and then you can't equalise coming back up, that air's feeling less pressure in your ear as you come up through the water column, and therefore it's expanding and squeezing on your ear. Or even people have talked about fillings, haven't they, and teeth cavities. I've also done this, and then it's very painful because it fills this gap, and you have to equalise it, or you're going to...
If you have a cold, it can happen, and if you've got blocked up tubes, you can get nasty, painful ears. That's why you're not supposed to go diving if you have a cold.
Good advice. Thank you, Helen. Tony is with us and has a question about brains. Hello, Tony.
Hello, sir. Well, I don't know what to think about this. A few years ago, they'd have said it was impossible to have given you a new heart, wouldn't they? But I just wondered if they'll ever be able to do anything with the brain as regards transplants. Are the various parts separate, like the memory and the so on? The sort of coils to look at, but you would know how they fit together.
Indeed, so the big question being, if we were to try to transplant a piece of brain from one person into another, what would be the consequence? Well, actually, scientists have done this in a number of ways. In one instance, there was a complete head transplant done for a chimpanzee, where the brain and head from one animal was grafted onto the blood vessels of another recipient body. Now, that's all well and good in the sense that it keeps the brain alive because the blood supply is preserved, but what it does involve is severing the connection between the brain and the spinal cord, which is how all the information gets into and out of the brain, pretty much. And that means that the animal is destined to have no mobility and no ability to feel incoming information from the rest of its body. So scientists, if they were going to do head transplants, would have to surmount that one. But there are limited neuronal grafting and transplant studies being done because there are some neurological diseases, neurodegenerative diseases, which are associated with the death or loss of certain subclasses or groups of nerve cells in the brain. And so scientists have reasoned that if you're losing certain populations of cells from the brain, perhaps what we need to do is to put new cells back into that bit of the brain, and perhaps they'll wire in and they can do the job that the cells that have been lost used to do. And a good example of this is Parkinson's disease, because we know that one specific group of cells that make the chemical dopamine get lost from the brain in this disease. And scientists have done a number of experiments where they go to fetal brain tissue, and you need fetal brain tissue because this seems to be critical because the cells seem to have a more robust phenotype. They seem to survive better. And if you harvest those cells that are destined to become dopamine-producing nerve cells in fetuses, and you put those into the adult brain of an individual with Parkinson's disease, and you put them into the part of the brain that is lacking dopamine, in other words, is affected by the disease, the cells seem to have the ability to survive to a limited extent and also wire themselves in to a limited extent and produce dopamine to make up for the shortfall. So scientists are doing that with with Parkinson's disease. They are also looking at the disease Huntington's disease, which is another neurodegenerative disease, but is caused by the loss of a different class of nerve cells. So they're trying similar tricks there. So it's early days. The results have been mixed, but they do show promise, and so we think that there is a reason to be pursuing this anyway. But it's a good question. Thank you very much, Tony. This is The Naked Scientist. It's Chris Smith and it's Helen Scales. We're answering your science questions. If you'd like to get in touch, you can send us an email, chris@thenakedscientist.com, or Twitter at us. It's @nakedscientist. Helen, Ace says, and I quote, "Why do we have finger and toenails?"
Well, I think some people would answer so they can paint them, so they're very pretty, and that they can be part of the way you attract a mate. But in fact, if you look around lots of different animals that we're related to, lots of other mammals, they also have fingernails or claws sometimes, and they're all very useful. And we also have them essentially, probably because they are tools. If you think back to our ancestors when we first evolved as humans, fingernails can be very useful for picking the skin off a fruit, for scratching a scratch. I mean, really just imagine if you didn't have fingernails or toenails, and I've lost a couple of toenails in my time, and it's not only very painful,
Oof.
How?
Did you drop something on them?
I did. I dropped a kettle not full of water on my toe,
Oof.
my big toe, and I lost that. It was horrible.
Lost your toe?
No, I lost my toenail.
Just the toenail?
It did grow back. The toe and the toenail, no, just the toenail. But no, they're very useful. And if you put a plaster over a sticking plaster over your fingernails or some sellotape, and see how you lose that ability to use your nails as tools. So that's probably why we still have them. Why do we have toenails? Probably because our ancestors, if you can imagine, chimpanzee-like creatures also use their feet for manipulating objects, and a toe would help to give you a grip on that. So really, they're tools. They're 10 little tools for us to use little tools for us to use in our daily lives, and that's why we still have them. And indeed, I'm glad we do. I think it's very painful without them.
Oh, we would all look much worse without fingernails that we could paint. I agree.
Exactly, but I do get muck under mine when I go gardening, which isn't so good either.
And possibly other things as well. Don't bite your nails afterwards, because that's
No.
how people catch things like toxoplasmosis
I don't
and other
indeed.
soil-dwelling parasites. So be
Nasty.
careful.
Okay, I will.
This is The Naked Scientist. We're answering your science questions. And Alejandro is on the phone with a question. Hello, Alejandro.
Hello. How are you?
Very good, thank you. What would you like to ask us?
I want to know, is it possible to change a battery wirelessly?
To change or to charge?
To charge, sorry.
Indeed. Well, yes, the answer is it definitely is, and people are doing exactly that with things like toothbrushes. You might have seen these toothbrush devices where you plug the toothbrush device into some kind of base station or holder, but there's no obvious electrodes. And what's going on there is it's using a magnetic field to convey the energy from the base station into the handset, and then from there into the battery. So what you do is have a coil in the base station which passes an electric current through it, generating a magnetic field, and you pass an alternating current through it so that the magnetic field is changing. You then have in the base of the object you want to charge another coil which you put into the magnetic field which is created by the base station. That's what's happening when you're docking one into the other. The magnetic field in the device therefore the magnetic coil in the device therefore sees this changing magnetic field, which induces an electrical current in the handheld device. That current is then fed into some kind of rectifier to turn an alternating current into a direct current, and it's then used to charge a battery. And that happens with things like toothbrushes. There are certain shavers that work the same way. Doing it over a greater distance would be really, really inefficient because the magnetic field decays as a 1 over r squared, so inverse square law, over distance, and therefore the amount of energy you'd have to put into the coil would be huge in order to charge things at a remote distance. So it's useful over small distances. It's not very good over short distances. But it's a good question. Thank you very much. Helen, got a question here for you from Colin McKenzie. He says, I live in California. I like lobsters. Why is it that there are lots of lobsters in the Atlantic but none in the Pacific? Could they be introduced there and thrive? And if not, why not?
Well, I'm afraid, in fact, that there are lobsters in the Pacific. In fact, there are various different species of spiny lobsters which don't have big claws, like the American lobster, Homerus americanus, does have big claws. That's the one in the Atlantic. But there are some spiny lobsters, including the California or red rock lobster, Panulirus interruptus. And there's also one called the green spiny lobster. And they do live on the Pacific, from California down through to Peru and out into the Pacific as far as the Galapagos. So there are various species that do live there, but by the sounds of it, they aren't around for you to eat, because I assume when you say you like lobsters, you like to eat them, and that's fair enough. They can be quite tasty, but some populations of lobsters around the world are very heavily fished and therefore aren't in population sizes that mean there's lots of them around for us to carry on eating. And that could well be the case in California for some of these species. Although, in fact, down in Mexico, in Baja California, there is a fishery for the red rock lobster, which has recently, about 5 years ago, was labelled as sustainable by the Marine Stewardship Council, saying that the fishermen down there are keeping within sustainable levels of catches so that there should be a healthy population in years to come. So if you do want to eat Pacific lobsters, I would definitely send you down to Mexico to try out the red rock lobsters down there.
Get some good margaritas too.
Yeah, excellent, absolutely.
It is The Naked Scientist with Chris Smith and with Helen Scales, and we're answering all your science questions. On the way, we'll find out what's been happening at the Cambridge Science Festival this year. Mira Lingham's been down there, and Ben and Dave will also be demonstrating how you make a tornado out of flames.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and Helen Scales. Now, this week, Cambridge has been buzzing, at least scientifically speaking, because the UK's largest free science festival, which is organised by the University of Cambridge, has been taking place. And Mira Lingham's been along to take a look.
This week saw the start of the Cambridge Science Festival, and so I've come along to one of the main event days, which is Science on Saturday. I've kicked things off today by visiting the Plant Sciences Department, and with me to tell me more is Jim Hasselhoff from the Plant Sciences Department here at the University of Cambridge.
The theme of this year's Science Festival is diverse science, looking at diversity in development, diversity in physiology, diversity in properties of plants. Within the tent, we've got quite a range of activities. Carnivorous plants, there's a display of seed and flowers, synthetic biology and application to engineering of plants, both now and in the future. So it's essentially thinking of how living systems work and how you might tweak or adjust them in the same way you might adjust a plant to produce more drug for drug production or to improve production for bioenergy or for food production, for example.
The point of the festival is to kind of make things a bit hands-on and interactive. So what are the key hands-on activities that you've got here today? Because I've seen children looking in microscopes and handling mushrooms.
They range from just the observation of biological systems, so looking at fungi and plants and algae, through to a giant flower that children can crawl into, and the giant flower is full of nectar in the form of sweets, and they have pollen in the form of glitter, and the kids dress up in bee suits and crawl into the flower and do the job a bee does, essentially.
Actually, that's just behind us now, I think, and it's quite popular.
It's extremely popular, and building your own fantasy seeds, so which you can use to build various motifs you see in seeds. We've got interactive reprogramming of floral structures.
So lots going on.
Yeah, it's all fun.
So I've stepped away from the plants now, and I've decided to try and come back in time by visiting the time truck activity here at the festival. And with me is Gareth Fabro, who's a student at the Earth Sciences department here at Cambridge. Hello, Gareth.
Hello.
What are the main aims of the time truck here today?
Mainly, we want to bring out rocks and fossils, which are normally kept in museums behind glass, and allow people to actually touch them and interact with them and get a closer look. We have bits of all types of earth science, so we've got some fossils with some dinosaur pieces, we have some rocks and minerals, and we also have a volcano. But it's generally to think more about our planet, how it's put together, and what it was like in the past, and how we can tell that, more importantly.
So we're actually standing now by your favourite hands-on activity that's here today, and it's a very large dinosaur foot.
Well, this is from an Albertosaurus, which is like a T-Rex, but a bit smaller. But the foot is still about 2 feet long and has sharp claws on the end. And I also have here a chicken's foot. And if you can compare the two, they both have 3 toes, and they both have the same amount of bones in their toes, and they have similar claws on the end. Obviously, the chicken's foot is a lot smaller. So from that, we can deduce that dinosaurs evolved into birds. Of that and lots of other bits of evidence as well.
I was just heading over to the pit building, but on my way I've just stumbled across a Formula One car in the middle of a car park. So I'm now here with Gordon Day, who works with the Williams F1 team.
Williams and Cambridge University Press have done an educational software package for a primary school called Race to Learn, and we're demonstrating one of the modules for Race to Learn here at the festival. We've brought a racing car as well so that we can show everyone coming through a racing car up close.
So tell me a bit more about this Formula One car, because it looks fantastic.
This Formula One car is from 2003. It's an FW25, and it was raced by Juan Pablo Montoya and Ralf Schumacher.
Wow. Tell me a bit about the actual stats of the car.
It has a BMW engine. It can go up to 250 miles an hour easily.
Where the driver sits, just in front, there's lots of different coloured buttons. So these obviously control very crucial aspects of the car.
That's right. It looks a bit like the cockpit on a fighter plane with lots of controls for the driver. And they control the various systems on the car. Plus, he can push a radio button to talk to the pit. And there's even a drinks button so that delivers a drink to him through his helmet.
Very clever. So lots of technology involved here.
A lot of technology indeed.
How would you say the visitors have been reacting to the car then? I mean, I'm just quite surprised to see it here.
Well, I've been answering lots of questions all day so far. I think they really enjoy seeing a Formula One car up close. A lot of the detail, the aerodynamic detail, is not easily seen on the television, and people have commented that coming up close and seeing that is quite something, quite amazing.
Hello, my name is Thomas Abbott, and I am standing next to a Formula One car.
Have you learnt anything about it that you maybe didn't know before? Or is there anything that you learnt about it that's quite surprising?
Though their pit stops are around 3 seconds now. Yeah, it's like it stops and then zzz, and all the tyres are off. And they've got a board underneath, so if it goes too low, then quite a lot of the board will be scraped, so they know they have to make it higher.
Has this made you want to be a Formula One driver?
I've always wanted to be a Formula One driver.
It's been a long day here at the festival, and I have to admit I'm very hungry. So I found out about a food factory that's going on at the pit building. From what I can see, there are children everywhere making lots of bags of cereal. And here to tell me more about how they're making these is Holly Marjarison, who's from the Human Nutrition Unit at the Medical Research Council here in Cambridge. Hello, Holly.
Hi there. Well, we're basically trying to show children what actually goes into the food that they're eating. So a lot of children will go into a supermarket, pick up a cereal box from the supermarket shelf, take it home and eat it, but not really know what's actually going into it. So we're showing them that there are the malt extract, the added salt and sugar for flavouring that goes into the cereal. We're also showing them the iron and the 6 different B vitamins that are going into their cornflakes. Not only that, though, we're also showing them that, not all food processing is bad, and that making cornflakes takes quite a long time, as they're finding today. The children are removing the bran and germ from the corn. They're adding different vitamins and minerals to the corn. They're drying them, they're rolling them out, they're toasting them. And we've even got our own tasting panel so they can try different makes and brands of cornflakes to see which ones they prefer.
I can hear a hairdryer going in the background and a lot of pounding. So I'm assuming the pounding is to kind of combine it all together. And the hairdrying, is that another way of toasting them?
No, we're actually toasting them in the oven. The cooking and drying stage that they do in industry, they do in huge steam dryers. Obviously, we're trying to bring it down to the Blue Peter level, if you like. So we're using hair dryers just to dry the corn off. And then they use the rolling pins to roll out the corn. But as you can hear, the corn can be very tough to roll. So they're banging the corn first and then giving it a roll to make it into a flake.
Which child here do you think I can convince to give me their cereal box? I'm very hungry.
I think they're all very prized possessions now. You might be hard-pushed to get one yourself.
OK, well, I can hope. What are your names?
Carl and Robert.
First of all, Carl, what have you learnt today about just what goes into your cereal?
I've learnt how they extract the vitamins, then they put them back in, and I found that quite intriguing.
And why do they extract it and then just put them back again?
They extract them because then it makes the cooking process much more easier.
And how about you, Robert? What have you learnt about the cereal production process today?
Well, I learned that lots of different makes of cereals have different tastes and different amount of vitamins in, which was actually quite surprising because not all cornflakes taste the same.
So have you got your cereal with you now, or are you waiting for it to be toasted? What stage are you at?
I'm waiting for it to be baked at the moment.
And what about you, Carl?
I'm also waiting it to be baked.
Can I tempt you to give me any of your cereal? I'm very hungry.
Yes.
OK, then.
Jackpot. So I'm going to be here now waiting for them to give me some of their toasted cereal. But otherwise, that's it from me at the festival.
That was Mira Smith-Ellingham having fun at this year's Cambridge Science Festival.
Now, Helen, I've got a couple of feedback emails here. Matthew Johnson says, I'm a science geek and I love the diversity of topics that you talk about. And Sorin Timar says he's actually listening in Bucharest in Romania. He says he's downloaded over 200 hours of the Naked Scientist podcast. That's nakedscientist.com/podcast. He says he's downloaded them all the way back to 2005 and he's listening to them at work and while he's commuting to work. Sorin, we'll send the ambulance along because clearly you are insane if you've managed to listen to 200 hours of the programme. So thank you for your support.
Very dedicated. We've also heard from Gerald after my story about fingernails, my question about fingernails, and he says that fingernails are also needed to act as a pressure pad. Primates, like ourselves, that pick up objects have flat nails. Otherwise, you'd be putting lots of pressure onto a very small surface area, and if we had claws, that would really get in the way. And there are marmosets and lemurs which have claws, but old world monkeys have nails like us, and the marmosets and the lemurs can pick up objects, but they don't have the grip that fingertips compared to claws. So essentially monkeys can hang on, the older monkeys can hang on, and that's another good reason for why we have fingernails. So thank you very much indeed for your feedback. Thanks, Gerald.
Thank you, Helen. Someone who else has been hanging on is Christine. She's on the telephone. Hello, Christine.
Hello.
Welcome to The Naked Scientist. How can we help you?
Well, I was driving home from work and looking at a glorious wintry sunset and thought what a perfect circle the sun was, and then it got me thinking, why are all planets and stars like the sun perfectly spherical? Why aren't they elliptical or irregular shapes? And I wondered what made them form that way.
So why are all these things round? What's the process that makes them want to be round? Yes, it's a very good question, and there's obviously some important science there for the simple reason that it doesn't matter pretty much what you look at. Most of these objects are round, absolutely. Well, the answer is it's gravity. And if we take our own solar system as a really good example, you have the sun in the centre, and that's round. And the reason that's round is because a big ball of gas collapsed in on itself and squeezed hard enough to start fusion. And around that ball of gas would have been another, initially envelope, like a shroud of material, dust, debris and gas, which slowly condensed into a disk called a protoplanetary disk. And over time, all this material is moving and jostling. Gravity, which which is a function of mass, would have pulled these objects slowly together, and they would have done what's called a accrete, or get together, and slowly would have built up planetesimals, miniature planets, and then they grew to make big planets as they hoovered up under increasingly powerful gravitational fields, the rest of that residual material. But because gravity is pulling things together, everything that's being attracted wants to get as close to everything else as it can do. And the most effective way for that to happen is if objects are spherical. It's the same as a raindrop, really, because water wants to get as close to other water molecules as it can without being in contact with too much air. So that's why raindrops form round blobs, not a flat sheet of water, because that's the way that as many water molecules can get as close together and stick together as they can. And that's what's happening with these newly nascent planets or other objects in space. The material squeezes together, and the way in which you can get as much material in as close a configuration as possible to other objects is if it's a round shape. Now, if you go in at high resolution and look closely, obviously there's not a perfect round surface because the Earth has mountains and things, and so does Mars. It's got Olympus Mons, a giant volcano. But to all intents and purposes, at low resolution, these things are round because gravity has made them that way. Thank you. Brilliant question. That was Christine Watchorn. Now, Helen, I've got a good one here for you, which is Bert Johnson says, how resilient are our oceans to overfishing?
It's a great question, absolutely, and it's something that's being talked about more and more in the news as we hear about the emptying oceans and fish stocks being depleted. And in fact, I had a look at his email, and he comes up with a nice idea, and in fact, a brilliant idea of, well, couldn't we actually just give the oceans a rest? And if we perhaps blocked off bits of area of the ocean for fishing for, say, 10 years or so, we could rotate around and the oceans would replenish themselves. Could they? Well, yes, well, they could indeed. In fact, what you're talking about are marine protected areas or marine reserves, and it's the sort of tool for ocean management that really is being talked about more by governments and by conservation groups, because we know that if you leave a piece of sea alone from the impacts of us people trying to catch all the fish that are there, it will just very quickly, in fact, recover. It's extraordinary how resilient the oceans, in fact, can be, and it does offer us some hope. The question is, can we actually get this done? I love the idea of blocking off, rotating parts of the ocean that we can have as these protected areas. If only it would happen. At the moment, less than 1% of the oceans are protected from human activities, and there are various estimates as to how much we should protect in order to have a resilient ocean that keeps itself going, and that's up to as much as 30%, a third of the oceans. If we could do that, then we would have much better chance of ensuring that fish stocks and all sorts of other marine creatures will still be around in years to come. So let's hope we can do that, and then we can achieve resilience in the ocean, because I think it will fight back, but we need to give it a helping hand.
Absolutely. Fred in Fox Street says, how far away is the sun from the moon? Well, the moon is pretty close. It's about 250,000 miles to the moon, and it's about 100 million miles to the sun, give or take. So when the moon is on one side of the Earth, and therefore closest to the sun, it's about 99 and 3/4 million miles between the moon and the sun. And when it's around the other side, so the Earth is between the sun and the moon, then you've got to add it on. So it's about 100 million plus about 250,000 miles, so 100 million and 250,000 miles between the sun and the moon. Helen.
Well, I think it's time for this week's Kitchen Science. But before we go over to Ben and Dave this week, last week they were explaining how they can make a mini solar cell at home simply by exposing the inner workings of an old diode to sunlight. Well, we've had an email from Randy Heisch, who has taken it a step further and soldered a few pieces of these simple cells together and used them to power a digital clock. He tells us he's been an engineer for 30 years and he never realised there's a good reason why diodes are encased in black epoxy. Circuit design would be a bit more challenging if you had to include light compensation into your design, he tells us. Randy also sent us some incredible pictures of his clock powered with just 4 exposed diodes, and we've put them up at thenakedscientist.com/kitchen science. So thanks very much, Randy. That's fantastic. But now let's get over to Ben and Dave for one of Dave's favourite experiments.
It's Science Festival time again, so I've come to Dave's garage where we're surrounded by boxes of experiments that he will be wheeling out throughout the Science Festival to amaze and delight the crowds. Now, Dave, every year you do lots and lots of experiments, but have you got one that you'd like to show us for Kitchen Science this week?
Well, this is one of my favourite and most beautiful of my experiments, and it's called the Flame Tornado.
Now, this is also quite special because we, in fact, are doing it on stage as part of the Naked Scientist Chris Packett fireworks show.
That's right, and as well as being really impressive, it also demonstrates some really nice physics.
Well, a flame tornado, a fire tornado, does sound very exciting. What do we actually need to do to set it up?
Well, the first thing we need is some fire. I'm going to light a fire in the centre of a small turntable, a bit like one of those Lazy Susan things you get to move food round on a dinner table.
Now I can see that you've actually nailed down an old jam jar lid on there. I assume that's just to keep the fire contained and keep it in the middle of the Lazy Susan rather than spreading out all over your garage.
And particularly all over my feet, yes.
OK, now as the fuel for your fire, you're using barbecue lighter gel. I've not really seen this before. Is this just like normal lighter fluid, but sticky?
Yeah, basically sticky so it doesn't fly around so easily. It's a bit safer.
OK, and we'll get that lit. And now we have a very well-contained fire on your Lazy Susan on the floor. I don't see anything that resembles a tornado just yet.
It's not especially exciting at the moment. What's happening is the fire is heating up the air's expanding. That makes it less dense, which means it's floating upwards, so the flames are moving upwards, as you'd expect.
And it's got to about 6 or 7 inches tall. You can definitely feel the heat above the flame. But so far, this is just a fire.
That's right, and if I spin the turntable at the moment, not a lot happens.
Well, no, not really. The flame wobbled about a bit as you were spinning it, but it didn't do anything else. It's still just a fire, but now a spinning fire.
OK, now when the air is rising upwards in the flames, air must be coming in to replace it, in from the side. So the trick is to make that air spin. The way I'm going to do that is by adding a cylinder of grill, so about a 1mm grill, over the outside and spin that grill.
So it's like you've put a very tall cylindrical sieve around the flame, and this should make the air spin while the flame inside it is spinning. So let's get that turning.
As you can see, the flame is spinning. Looks really quite cool. And it's got about 3 or 4 times longer. It's now about 1 metre high.
That is impressive. That is a tornado of fire. You could feel the heat from the safe distance away I was as well. What's going on there? Why does spinning it and having this grill in place make the flame so much taller and so much more exciting?
Well, the first thing which is going on is that the flame is spinning much, much faster than this cylinder of sieve. And the reason for that is the same reason why, if you've ever played on a roundabout when you were a kid, when you climbed into the middle of that roundabout, the roundabout spins faster and faster and faster.
Yes, it's actually quite hard to pull yourself into the middle. You feel it being pushed out, but when you get there, oh boy, do you spin.
That's right, there's 2 effects. One of them is that as you move your weight inwards, it's got less distance to travel, so it'll take less time to go round, and also it takes all that effort to climb in, and actually all that energy you're putting in is speeding you up.
Why isn't the flame being pushed outwards, like I would be if I was trying to get into the middle of the roundabout?
The simple answer to that is it is. But in the centre of the fire, the air pressure is much lower than everywhere else because there's a big column of hotter, lighter air above it. So the pressure is lower, which counteracts the centrifugal force, which is throwing you outwards.
OK, so the differences in pressure mean that the flame doesn't get thrown outwards, which I must say I'm quite relieved about. But why does the flame itself get so much taller?
There's a couple of effects. One of them is right down at the bottom where the fuel is. The air's moving a lot faster, which means a lot more fuel gets evaporated, so there's a lot more fuel in the flame. And the other one is this centrifugal force. Because the air is being thrown outwards all the time, it's very hard for air to get in and mix with the fuel. So the fuel burns much more slowly. So it carries on burning for longer, to get a much longer flame. If you looked at the top, it turned into a very, very sooty flame because it wasn't entirely burning because of this shortage of air.
So rather than burning out after about 6 inches or so, you're restricting the oxygen to it, which allows it to get to, it was over 1 metre. It was really a very tall flame.
That's right, and this is exactly the same way that a hurricane works, but with less fire.
Well, hopefully less fire at least.
A hurricane forms over very, very hot water, somewhere like the Atlantic off West Africa. That produces lots of warm air above it, warm, moist air, which floats upwards, draws in air from thousands of kilometres away. Because the Earth is spinning, that air is spinning. As it moves towards the centre, it spins faster and faster and faster, so you get absolutely lethal winds, which can create huge amounts of damage.
So if the Earth wasn't spinning, we wouldn't get these hurricanes. It would be a bit like the 6-inch flame that we had to start with.
Yeah, you're right, and the same's true about less powerful upwellings of air, like low-pressure areas coming off the Atlantic. So if the Earth wasn't spinning, we'd have hardly any wind at all.
So a spinning torrent of fire can actually explain how hurricanes work, as well as being very impressive. That's all for Kitchen Science this week. We'll be back with another experiment next week.
Thank you very much to Ben and to Dave. And incidentally, the fire draws the air in from the side, and if that air's spinning, then it can end up with a genuine tornado of fire. So one of the things that you can also do is to have a look at our website, which is at thenakedscientist.com/kitchen science if you want to find out more. And we also heard from Nat Spirit in Second Life, who says fire is a very good start for kitchen science, as ever. Helen.
We've heard from Tommy on the forum, who's got a question that I actually really want to know the answer to, because I hadn't even thought of this until now, and that is, why does hot water sound different to cold water when it's poured? And now I come to think of it, a cup of tea, when I'm pouring it, does sound different to a glass of water, and why is that?
Indeed, and your shower will sound different too. If you've noticed, when you turn the shower on in the morning, the cold water comes through from the pipe first. It will splash and sound different against the bottom of the shower to when the hot water, which comes along shortly afterwards, comes in. The note will change. And this is a real observation. Your ears aren't deceiving you. The reason for it is that water changes its viscosity, its stickiness, according to its temperature. So if you could zoom in with a microscope, really powerful microscope, and look at some water molecules, what you'd see is they were shaped like miniature boomerangs. And at the apex of the boomerang, you would see an oxygen atom, and at the arms, you'd see a hydrogen atom. And the oxygen loves electrons, so it pulls the electrons of itself and the hydrogen towards itself very tightly, and that makes the oxygen a bit minus. The hydrogens are correspondingly, therefore, a bit plus. And so, as a result, when the molecules are sitting together side by side in solution, the positively charged hydrogens are attracted to the negatively charged oxygens of an adjacent molecule. And this is called hydrogen bonding. And it makes water sticky, and it gives it some of its special properties that, in fact, help it to make life happen as well on Earth. So it's pretty important that this happens. But when you heat the water up, the particles start to move much more quickly. They have more kinetic energy, which is a function of the temperature. And this means that they're zipping past each other much faster. They're therefore gluing onto each other less well, and this makes the water runnier or less viscous. So when it comes splashing out of the shower and hits the shower pan, the water fragments into smaller particles and makes a higher-pitched splashing noise than when it goes into the cup or goes into the sink when it's cold. So have a listen next time you're in the bath or the shower, and you will see that the note is different.
There you go, science of a cup of tea, and that's one of my favourite things, so that's wonderful.
Distilling the best science. The Naked Scientists.
This is The Naked Scientists with Chris Smith and Helen Scales. We're answering all your science questions.
Right. Well, I hope it's not because they think that our show is as interesting as watching paint dry. But we've got a question from Owen who wants to know, how does my paint change colour as it dries?
Yeah, now that's a fantastic question. It's the same science, actually, behind why clothes look a bit darker when they're wet than when they're dry. And the reason that this happens is because when you have paint in the tin, the paint is mixed with some kind of solvent, water or oil or something, which makes the paint easy to spread onto the surface so you get a nice even coat. So when you paint the paint onto the wall, it's got all that solvent in it. The solvent then evaporates off or dries, and this leaves behind the particles of paint on the wall. Now the particles, if we take white paint as an example, that's usually titanium oxide. Very, very white. Those particles are roughly the same wavelength, same size as the wavelength of light, which is why they reflect and scatter lots and lots of light back at you, which is why you see a white surface. But when the paint is wet, those particles are surrounded by little droplets of water or oil. That's the solvent. And so when light goes in, it doesn't see these tiny particles of roughly the same size as the light wavelength. It gets subjected to a bit of refraction through the fluid, the liquid, and that buries it deeper into the wall surface rather than reflecting it back out at you. So if it's darker, of course, what must be happening is less light is being scattered back towards you than being absorbed, and that's why it looks darker. Once that effect goes away and you've just got the particles there, you're scattering more light back at you, so the paint actually looks brighter.
And you thought drying paint was dull? Absolutely not. Another question here, and I'm dying to know this because this is something I've wondered about for a while, is how do odour-abating insoles work? How do we stop our shoes, our trainers, from being quite so disgusting and stinky?
Yes.
That's a question from Craig. Thanks, Craig.
OK, well, most of them have got activated charcoal in them, and all that means is that it's charcoal with a big surface area. And this means you've got carbon, which can soak up noxious odours, so you have something that can lock away odours. That's the first point. And it will also do another thing, which is soak up water. Now, your feet squirt into your socks something like 1/4 to 1/2 litre of sweat every day. At the same time, you've got skin cells falling off at the rate of thousands every second from all parts of your body, but your feet especially, because the skin on your feet is a bit thicker. So what you've got is all of the elements of the perfect microbiological or bacterial banquet going on your feet. You've got food in the form of dead cells, you've got water in the form of sweat, and you have warmth. And all those things add together to very active, hungry bacteria being well fed. And they produce various chemicals, some of which are whiffy. They're smelly, they're volatiles. So if you put these odour-eating things into your shoes, they soak up the water for a start, which means that there's less to keep the bacteria lubricated so they don't grow as well. And they also soak up some of the noxious gases because they have a big surface area and they can absorb those materials, and that stops them being so pungent. So they work in a number of ways, but that's chiefly how it does it.
Well, there you go. It's the science of smelly feet, or not.
Now, I've got a quick one for you, Helen, because Nazza says, how do Portuguese man-o'-war jellyfish reproduce?
Ah, wonderful creatures indeed. Although keep your distance, of course, because they are nasty stingers, but they're beautiful things to look at. And I think the reason for his question is based on he knows that they are not, in fact, jellyfish. They're not single living creatures like that, but they're colonies of lots of little creatures that live together. They're related. They're in the same phylum, the Cnidaria, as jellyfish, and they look similar, but they are, in fact, different. They're called siphonophores. And yes, they're made up of lots of different types of, three main different types, actually, of little cells that all animals that live together. There are dactylozooids, which make up the tentacles. There are gastrozooids, which are the bits that eat the food. And there are gonozooids, and they are the bits of these creatures that reproduce. They produce sperm and they produce eggs. In fact, you get female and male Portuguese man-of-war, and even though they're called men. And they will then fertilise in the water to produce larvae, which grow into bigger Portuguese man-of-war. And the way that they grow from those individual cells is by asexual division of those cells, and they produce all those individual three types of animals that live in this one colony and drift around the oceans, stinging things and eating things as they go.
Brilliant. I'd actually always wondered that, because everyone says they're this cluster of things. How do they all reproduce? But it's a really good question. Thank you for the lovely answer. Talking of lovely answers, Diana, not that you're going to give us a lovely answer quite yet, you've got to give us a question first, but it's time for this week's question of the week.
Yes, this week, just how much can you actually learn in your sleep?
My name is Julie Lonnie Chang, and I live in Davis, California, and I have a question. My question is there any science to the companies that sells or claim that their subliminal CDs could actually alter your behavior simply by tapping into your unconscious mind?
So, do these CDs work, or do they just deprive their listeners of much-needed sleep?
I'm Ian McLaren. I'm Professor of Cognitive Psychology at the University of Exeter. The answer to this question is no, but with a hint of yes to it. I'll start with the bad news, that these CDs are unlikely to be an easy way to acquire new knowledge, such as a new language, for example, before considering evidence for subliminal learning itself. Subliminal learning means learning that takes place below the normal threshold for awareness. An example would be learning a list of words by listening to them while you were asleep. If you were able to recall the words afterwards, when you were awake, then that would be evidence for subliminal learning. The problem with demonstrations of this kind, and there have been some, is that there is often insufficient control to ensure that the listener is really asleep. When these studies are done well using EEG monitoring to ensure that the subject is genuinely asleep, the results tend to be unimpressive. There is little evidence of above-chance recall of the words, so in this sense, these CDs are unlikely to work. There is, however, some evidence for a different kind of learning under subliminal conditions. Even though the listener cannot recall the words, we can show that they have had a detectable impact on them. We use a different test in which I ask you to say the first word that comes into your mind after I give you a cue word. Imagine the list you'd been exposed to contained the word traffic. If I now cue you with the word jam, you'll be quite likely to offer traffic as a response. But if the list had instead contained the word strawberry, then that would be the more likely response to my cue. This effect does seem to occur after subliminal presentation of words. Psychologists see it as an example of priming, where experience of a word makes it more accessible, more readily available in some way. But this is not new learning. It's better thought of as a modulation of memories that you already have. So I'm afraid this yes part of my answer is not likely to be terribly useful to you when it comes to acquiring new information.
So there's little evidence subliminal learning CDs will teach you all that much in your sleep. They can, however, improve your recall of certain words and associations.
On our forum, we had all sorts of chat about the legislation against subliminal advertising in movies, which has been banned in some places, but there's little evidence of it having any really significant effect anyway. You're On wrote about backmasking in Led Zeppelin songs, perhaps suggesting that some hidden backwards phrases about Satan got them to number one. And Discover Dave said that if you can't make out words clearly anyway, it's unlikely your brain can make sense of them, meaning you won't be influenced.
But now I shall use the power of radio to suggest that you're all hungry enough to consider this question.
Hi, my name is Harriet Dickinson from Cambridge, and I want to know, are all the calories in food actually absorbed by the body?
Can we cut a little bit off the calorie count on the back of the chocolate bar? I hope so. Email your answers to chris@thenakedscientist.com or write them on the forum for us to read out at thenakedscientist.com/forum.
I bet there are a few people who are absolutely gagging to know the answer to that question. Thank you very much, Diana. That's Diana O'Carroll with this week's Question of the Week. And you can get hold of Question of the Week, including all of the past questions that we've answered, give or take, on our website at nakedscientist.com/QOTW, or you can find it as a podcast in its own right on iTunes. Otherwise, that is it for this week. Thank you very much to our wonderful production team, Ben Valsler, Mira Sinthalingam and Dave Ansell. We are back next week with a look at what the future holds for farming and how science can help to make a difference. And that includes looking at what climate change will probably do to farming and also how GMP plants might help to improve poorer soils. If you'd like to send in any thoughts, feedback, questions or comments on that, then you can send them in by email as ever, chris@thenakedscientist.com. In the meantime, have a very good week and see you next time. Goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.